Hello, welcome to Module 28 of the course on application of spectroscopic methods in molecular structure determination. In the previous three modules, we discussed about infrared spectroscopy, the fundamental aspects of it, and the application aspects of infrared spectroscopy also we discussed. We will make this as a tutorial session, in other words, a problem solving session based on infrared spectroscopy alone. Now, one does not always use only infrared spectroscopy to do any kind of a structural elucidation problem solving. The purpose of this particular module is to make you familiar with the infrared spectra so that various functional groups can be identified, and in terms of interpretation of the infrared spectrum, the familiarity is built up during the course of this tutorial session. Now here is the question. There is the infrared spectrum of a compound with the molecular formula C3H3Cl. What is the most probable structure that will fit this particular data? Now as you see the infrared spectrum, you need to understand the characteristic features of the infrared spectrum in this particular case. There is a sharp peak around 3250 or so in this particular region, and there is another sharp peak around 2100 and something, 2200 and some frequencies also there is a sharp peak, and there are other peaks also present in this particular system. So let us first focus on this particular peak, which corresponds to the 3300 inverse centimeter peak and the 2150 inverse centimeter peak also. Now this particular peak could suggest that this is a terminal acetylene CH stretching frequency. Please remember that among the various hybridization CH stretching frequency, the SP CH stretching frequency comes at the highest frequency, then comes the SP2, and then finally comes the SP3. So it could be that this is because of an acetylenic CH stretching frequency, a terminal acetylene CH stretching frequency. If that suspicion is true, then you should also have a C triple bond C stretching frequency. Indeed, you do have a C triple bond C stretching frequency coming at 2115 inverse centimeter, which is part of the T triple bond C acetylenic unit in this particular case. The molecule does not have any kind of OH or NH, so one cannot interpret this by mistake to a OH or an NH kind of a stretching frequency, because they also come in the same region. For example, a secondary amine can easily come in this region as a sharp peak like this, and that is not the case because the molecule does not possess any kind of a nitrogen. The molecule also has a double bond equivalence of 2. In other words, it is an unsaturated system with a double unsaturation. So a terminal acetylene can actually satisfy the unsaturation of this particular molecule, this case. Now finally the molecule has a chlorine, so the CCl should be seen somewhere. The CCl is actually seen as a stretching frequency in the region of 650 inverse centimeter. This peak is most likely due to the CCl kind of a stretching. So based on the problem, this is a very simple molecular formula. One can jot down the various possibilities and rule out one after the other. In doing so, for example, we look at the terminal CH of an acetylenic peak, and a C triple bond C of an acetylenic peak, and a CCl of the acetylenic peak is also seen in this particular case. So based on this, we suggest that this is actually propargyl chloride is the structure of the compound that would most likely fit the spectral data in this. The blue arrow indicating this particular frequency, which is looking like a doublet, could be because of the symmetrical and the asymmetrical stretching of the CH of the CH2 group. In other words, the sp3CH stretching frequency comes in this region somewhere around 2900 inverse centimeter or so. So this is how one tries to analyze and interpret the NMR, the infrared spectrum for a given molecular formula. First to find the degree of unsaturation and look at the most prominent peaks. These peaks are also prominent peaks, but then they probably come in the bending region of this molecule. So one does not interpret this in very detailed manner as far as the bending regions are concerned. Now the problem is stated here. The main constituent of cinnamon oil has the formula C9H8O. Identify its structure. One needs to know what is the main constituent of cinnamon oil. It could be cinnamaldehyde, it could be cinnamyl alcohol, it could be cinnamate ester, or it could be cinnamic acid. All the cinnamon based systems are written here, except cinnamic acid is not written here. Now among this formula ABC molecule, if you look at, the one that is cinnamaldehyde corresponds to C9H8O. So the molecular formula is satisfied for the cinnamaldehyde structure. But let us see whether the infrared spectrum also satisfies this particular structure one can easily rule out A and B because it doesn't fit in the molecular formula that is given. So the cinnamaldehyde probably best fits the structure. Compound C is cinnamaldehyde and it meets the expected molecular formula, that is good, and it is alpha beta unsaturated aldehyde and it is also a monosubstituted benzene derivative. So what one need to look in the NMR, sorry, not the NMR, I keep telling NMR, this IR spectrum is that one need to look at the aldehyde stretching frequency for an alpha beta unsaturated carbonyl functional group, and one needs to look at whether it is a disubstituted benzene derivative in terms of the out of plane bending mode of the monosubstituted derivative. One can also look for the CH stretching frequency of the aldehyde in the infrared spectrum. Now if you look at the highlighted areas clearly, it tells you that there is an aldehyde functional group, both an alpha beta unsaturated aldehyde functional or carbonyl stretching frequency 1677 corresponds to that. In fact, you can also see the C double bond C stretching frequency by the side of it because it is an alpha beta unsaturated system, and the CH stretching frequency of the aldehyde, which comes around 28 inverse centimeter as two line pattern, is also very clearly seen. And finally the monosubstituted benzene derivative, which has out of plane bending modes in this particular feature, is also reflected. So the spectrum actually reflects the features that would satisfy this particular molecule to be the correct molecule as far as the major constituent of the cinnamon oil is concerned, is cinnamaldehyde. Now there are 4 options given. One need to choose the correct option which will fit in this particular infrared spectrum. In other words, the IR spectrum belongs to one of the compounds listed below. Identify the compound that fits the spectrum. Now let us look at this spectrum, the structure of this compound. This is a saturated ester, and this is also a ester, but it is an alpha beta unsaturated ester. This is a saturated ketone, and this one is alpha beta unsaturated ester plus an unsaturation is also there. So if one were to look for an alpha beta unsaturated ester, the saturated ester comes around 1750, 1740 in inverse centimeter frequency, and if it were to be an alpha beta unsaturated system, it will come around 1720 or so. So one can expect the saturated ester to be ruled out because the carbonyl stretching frequency is actually seen at 1712, so this can be ruled out. One can also easily rule out the alpha beta unsaturated carbonyl ester functional group because this will not be less than 1720 or so. One can easily rule out this particular ester because this is a unsaturation is conjugating with the lone pair of oxygen here. It would in fact increase the frequency compared to the base value for an alpha beta unsaturated system. So this is a saturated ester functional group which is also 1745, which is higher than what is observed. So the one that fits the most is this saturated ketone, which is expected to come around 1710 or 1720 for a linear acyclic carbonyl functional group, which is a ketone. 1712 seem to match the spectrum correctly. So this particular region, essentially because it is an aromatic system, the C double bond C is also seen here. So one can very clearly rule out the possibility of ABC to be the wrong, ABD to be the wrong structure. So the correct structure is C for that particular spectrum. Let us move on. Now there are 4 structures again given here with one infrared spectrum. One has to match the spectrum to one of these structures that is given here. Now this is a secondary amine and this is a tertiary amine. So secondary amine should give only one peak in this region, but there are 2 peaks here, so one can easily rule out that it is not a secondary amine. Tertiary amine should not have any kind of an NH stretching frequency. This is NH stretching and this is the CH stretching region of the infrared spectrum. Because all of them are amino compound, we can conclude that one has to have a primary amine to account for the doublet kind of a structure that is given here. The NH primary amine gives both asymmetric as well as symmetric stretching frequency. That is why it comes at a doublet, which will be absent in the secondary amine as well as the tertiary amine. So A and B can be straight away ruled out on the basis of the NH stretching frequency being a doublet. So only C and D seem to fit the criteria. Now how do we decide whether it is a C or the D? That one has to depend upon the out of plane bending mode. If it is a para-disubstituted derivative of this kind, there will be only one band, out of plane bending band. If it is an ortho-substituted derivative like this, there will be 2 bands or more bands. So on that basis one can rule out C also. So the correct structure most likely is D, which is para-amino-ethyl benzene for this particular spectrum. Now this infrared spectrum, again there are 4 structures given here. and we have to fit in one of these structures to this particular infrared spectrum. Now if you look at the compounds, this is an alpha beta unsaturated ketone and this is a saturated acid. So one can easily rule out the saturated acid because there is no OH functional group in the molecule. So the absence of the OH stretching frequency in this region essentially rules out the possibility that it is a carboxylic acid. So B is ruled out. It can be a saturated aldehyde, but then this is not a saturated aldehyde value. Remember, saturated aldehyde should come around 1720 or 1710. This is around 1688. So the saturated ketone and saturated aldehyde can also be easily ruled out. So the only option is that you have a alpha beta unsaturated ketone. This is propiophenone is the molecule. Propiophenone has a frequency around 1688 because it is an alpha beta unsaturated ketone. Because it is a monosubstituted benzene derivative, it also has the out of plane bending modes which is coming in this particular region. So these are the most prominent observation that one needs to make in order to distinguish this. The fact that the carboxylic acid can be straight away ruled out is based on the fact that there is no OH stretching frequency. Carboxylic acids invariably give a very broad band in this particular region for a OH stretching frequency, which is absent. And one can also rule out on the basis of the fact it is not an aldehyde because the aldehyde CH stretching frequency is also not seen, which should come around 2800 inverse centimeter or so. So the correct structure for this infrared spectrum is A, which is propiophenone in this particular case. Here is another problem. The IR spectrum, there are 3 IR spectra given here and they belong to one of these polymers. Each one belongs to one of these polymers. So one need to match the IR spectrum with the correct identification of the polymer structure. The polymers given are PMMA, which is polymethyl methacrylate, which is a ester polymer. It's a saturated ester polymer. Nylon, which is a polyamide. So it should have an amide stretching frequency for this one. Polyacrylonitrile styrene copolymer, polystyrene polymer, polyethylene polymer. Now if you look at polyethylene polymer, this is a saturated CH2, CH2, CH2 kind of a chain. It is like a paraffin oil or like a Newjol kind of a system is what one should see. So if you look at the spectrum, the prominent peaks are CH peaks here and C double bond C peaks in this particular region. And again out of plane bending kind of a mode vibration is what is seen here. So these are the prominent features. So in fact polystyrene will fit in this particular system, but look carefully this particular band here. This band which is coming around 2200 or so corresponds to probably a nitrile kind of a functional group. So one is unmistakably one should identify this as a nitrile functional group. The only polymer in this series ABCD that has a nitrile functional group is the acrylonitrile styrene polymer. So it has a signature of both styrene as well as the acrylonitrile chain, which is a copolymer in this particular case. Suppose if this peak which is highlighted in red is missing, one can easily say that this belongs to polystyrene kind of a spectrum. One can rule out polyethylene in all of this because polyethylene will have a Newjol kind of a spectrum. It will have only a CH stretching frequency. Since it has C double bond C CO bond stretching frequencies, one can straight away rule out E as an option. D as an option is also ruled out now because the carbonyl functional groups are there in the other 2 spectra. So one can rule out D also in this particular case. So D and E are ruled out. One has to deal with ABC. Now we have identified this compound to be C, which is the polyacrylonitrile styrene. Let us come to the next spectrum, which has a carbonyl stretching frequency at 1730. 1730 is a saturated ester carbonyl stretching frequency. So most likely PMMA, in other words polymethyl methacrylate polyester, is responsible for this particular stretching frequency. Then we are left only with nylon, which is an amide. Amide has 2 carbonyl stretching frequency and also has an NH stretching frequency. In fact, one can see the NH as well as the CH stretching frequency in the region between 2800 to 3200 or so in this region, which is characteristic region for the NH and CH. And then there are 2 intense bands which are the amide bands. Amide band 1 and amide band 2 are seen very clearly in the case of polyamide. So the assignment is that this is polyacrylonitrile styrene copolymer. This is corresponding to PMMA, which is polymethyl methacrylate ester polymer, and finally B, nylon, which is a polyamide polymer, is this particular spectrum. Here is another problem. 3 IR spectra are given and 3 structures A, B, C are also given. one needs to match the spectra with the corresponding structure. Now if you look at ABC, this is a saturated gamma lactone, alpha beta gamma lactone. This is alpha beta unsaturated gamma lactone, and this is also unsaturated lactone, but except the unsaturation is in conjugation with the oxygen lone pair of the lactone rather than the carbonyl functional group. So based on the discussion we had in the earlier module, this would have the highest stretching frequency of the carbonyl stretching frequency in the IR spectrum. Then comes the saturated carbonyl stretching frequency of the saturated lactone, and then comes the alpha beta unsaturated lactone carbonyl stretching frequency. The stretching frequencies are marked for the carbonyl stretching in the IR spectrum. This is 1761, this is 1810, and this is 1773. So based on the argument, C should be this one which has the highest stretching frequency of 1810. So C corresponds to the middle spectrum here. A corresponds to the spectrum which is in the bottom, which is 1773, and B corresponds to the alpha beta unsaturated system, which has the lowest one around 1761. So the assignments are, this is B, this is C, and this is A in terms of the, so all you need to do in this particular case is to look at the carbonyl stretching frequency alone. Nothing else is necessary, in fact, to identify this system. In fact, the saturated, if you look at the alpha beta unsaturated system, you have the additional C double bond C. In this, C double bond C is here, and here the C double bond C is here, whereas this does not have any band corresponding to a C double bond C. So this is clearly the saturated system, unmistakably one can say, on the basis of C double bond O and the absence of C double bond C. Now the IR spectrum of cis and trans cyclohexenol is given here. One need to assign which one corresponds to which. Now one needs to understand a concept that when you have a stretching happening, in the case of the cis isomer, there will be a maximum change in the dipole moment compared to a trans isomer. So when you have a comparison of cis and trans isomer, you look at the CC stretching here. CC stretching will be maximum in the case of the intensity wise, it will be higher in the case of the cis isomer rather than the trans isomer. So this information is necessary to understand in order to have the assignment to be done properly. The intensity of the C double bond C stretch is stronger in the case of cis than in the case of trans due to the higher change in the dipole moment during the C double bond C stretching. The cis isomer also has the out of plane bending mode 700. This many people may not know this, but it is a very useful information. Whereas the trans one has the out of plane bending around 900 inverse centimeter. Both the CO stretch appear at 1000 inverse centimeter as well as OH stretch appear at C0. In other words, the OH stretching frequency as well as the CO stretching frequency, which is over here, they are not very useful because both of them have the hydroxy functional group and both of them will have the CO stretching functional group also. But if you look at the highlighted region here, which corresponds to the C double bond C stretching region, which is around 1600 inverse centimeter or so, the intensity here is much higher compared to the intensity here. So that will put this to be the cis isomer. And in addition to that, use the information, the out of plane bending for the cis is around 700 inverse centimeter and for the trans is around 900 inverse centimeter. So combine these two factors, the top spectrum corresponds to the trans isomer and the bottom spectrum definitely corresponds to the cis isomer because this has a higher intensity of the C double bond C. Another problem, interesting problem based on the carbonyl functional group assignment. You have alpha diketone. Remember, alpha diketone give only one band in the infrared spectrum. They don't give two bands because there are two carbonyl functional group. They have identical stretching frequency, so only one band is obtained. In the case of beta keto ester, beta keto ester exists in the enol form also. So they will also give the OH stretching frequency if it were to be present. The fact that there is no OH stretching frequency here rules out the beta keto ester as the possibility in this particular case. Acid chlorides also give only one stretching frequency. Remember, the anhydride, which gives the two stretching frequency, one corresponding to the symmetric, the other one corresponding asymmetric stretching frequency. So when you see a band like this around 1800-1750 region, definitely it is because of an anhydride. So one can straight away rule out the possibility of ABC for the spectrum. The structure D corresponds to the spectrum perfectly in terms of the fitting of the data for the two carbonyl stretching frequency in the region 1820 and 1750 corresponding to asymmetric and symmetric stretching frequencies of the anhydride system in this case. So no OH band, so rule out B. Two bands in the infrared carbonyl stretching frequency in the 1800 region definitely corresponds to the anhydride system. Here is a problem. The molecular formula is given. From the molecular formula, you can tell this molecule has degree of unsaturation of 2. And what is the name of the compound is what we are asking here. The double bond equivalence is 2. There is a cyano peak present here. Because there is a nitrogen present here, you will look for amine or the cyano. Cyano is definitely here because it is coming around 23-25 inverse centimeter. So that corresponds to the cyano functional group. So one of the nitrogen is cyano functional group. And you can also look whether there is a NH stretching frequency. NH is absent, so it cannot be primary amine or secondary amine. But you cannot rule out a tertiary amine possibility. In order to identify whether it is a tertiary amine, one can always look at the CN stretching region. CN stretching is fairly strong. This here, for example, the CN stretching region. So it could be a tertiary amine. So based on the molecular formula being a simple C5 molecular formula, if you rule out the primary amine, secondary amine, as well as the acetylene as an unsaturation, we will come up with a structure which corresponds to something like this. This is 3NN dimethyl amino propionitrile is the name of the structure of the compound that is shown here. This is most likely the structure which fits the molecular formula, which also fits the degree of unsaturation, which also fits the presence of a nitrile functional group with a CN stretching frequency, which gave a clue that it could be an amine also because there are 2 nitrogen present here. It cannot be a dinitrile compound because of the 2 nitrogen, because then the degree of unsaturation will be much higher than 2. It will become 4, for example. You cannot have more than 1 nitrile functional group. So the other nitrogen has to be an amino functional group. In the absence of the NH stretching frequency gave the clue that it could be a tertiary amine. So the tertiary amine is put in this particular to fit the molecular formula C5. This is the most likely structure that corresponds to this particular spectrum. So all the spectra are recorded that shown in this particular problem solving session is taken from this book, and I would like to thank you very much for your kind attention.